Nobody believes me when I say I'm nervous to get on stage. So here I am. Thank you. Well, thanks so much for having me here. Thank you all for being here. I want to talk about something that we deal with every single day, which is how do we write code? How do we write programs? What kind of methods can we apply? Just quickly, how many of us are programmers here? Of course, I'm in the right place. Let's talk about languages for just a minute before we get going. Just throw some names. What languages do you program in? Java, I heard. What else? Scala? Did they say Pascal, somebody? Scheme? What else? Kotlin? COBOL? Okay, what else? I won't even type that. Python. Let's put Python here somewhere. Python. PHP. What's wrong with this side of the room? No, just kidding. Absolutely fine. Well, let's put C++ here just for a minute. What else? Go. Okay. All right. So this is good start. This is good start. Anything else? TypeScript. Ooh, that's a good one. Let's put it right here for a minute. All right. Anything else? Of course, JavaScript, right? Okay. Let's leave that there. We'll come back to that and talk about it. So let's get going. So we want to talk about methodologies and paradigms, but let's start with the question, who are we? And I want to start with the question to think about who we are. And if you ask a group of people who we are, we're probably going to hear all kinds of things in this word. Programmers, coders, data scientists, developers, computer scientists, software engineer, architect, and more, managers, what have you. But I want to ask the question again, who are we really? And I'm going to say we're not any of those in reality. What we are really is, we are problem solvers. That's what we really do. We go to work every single day and we solve problems. I know what you're thinking. You're thinking, but some people create more problems than they solve. True. But still, we are problem solvers. That's what we do fundamentally. We are problem solvers. And in solving those problems every single day, programming is a very small part of that puzzle in solving the problem. Now, I love programming languages. I program in about 15 different languages. What I'm telling you in so many words is I'm not good in any one of them. But I love learning them. I love applying programming languages. But even though I'm so excited about programming and programming languages, I can't forget that that's still a small part of what we do, which is something bigger, which is solving problems and delivering value to our customers. But just focusing on the programming languages itself, languages play a role in solving those problems. And so the question to really ask is, languages, what are really languages? Well, it turns out languages really are a form of communication. They're a communication tool. And essentially, programming languages are a way to communicate with programming systems, but also to other fellow human beings that we work with. So it's really a communication tool. But one thing that really excites me about programming languages is that they are really a form of expression. And in all honesty, when I started programming about 35 years ago, I got excited about programming because there was math and science in it. But several decades later, I'm still interested in programming. And the reason for that is because of the art and the form of expression in programming. And this excites me because you could write a piece of code and then sit back and rewrite it, and you can refactor it, and then you can express in different ways and have a colleague of yours look at it and say, why don't we write it this way? And to me, that form of evolving the code to do the same thing, but to do it in so many different expressive ways is very exciting. And I have this absolute luxury, and I'm very thankful for this, is that I get to spend days sometimes, lock myself in a room, and write code and just sit there and refactor it with really no consequence, but to just see how the code evolves. And to have that luxury to see the code evolve is something that I'm very thankful for. But I enjoy watching this code evolve and take shape, and it's a form of expression. But we have so many different programming languages out there. Which one should we choose, and what is the relationship between the languages? Now, as programming languages, we see them. We often hear people tell us that languages are Turing complete. Most of them are. In fact, any programming language we want to use for general purpose programming better be Turing complete. But on the other hand, though, saying that a language is Turing complete is just not enough. Because to me, saying a language is Turing complete is like saying that most people can sing. Trust me, you don't want me to be singing on stage. That's going to be horrible. And I would never torture anybody with that. But just because humans can sing doesn't mean people like me can sing. So similarly, just because languages are Turing complete doesn't mean that those are the right languages for everything we do. And Turing completeness, unfortunately, doesn't answer a lot of other questions. For example, we could ask the question, is it easy to use? Is the language elegant? What about the performance this language provides in terms of code execution? What about efficiency of the code at runtime? And what about the usability of the code itself? And what about maintainability? Is it easier to maintain? And so many other questions are not answered. So when it comes to languages, we have to look a lot beyond these things, and we have to really use languages that's appropriate for what we do. But languages come in very different flavors. And this is one of the things that excites me about programming languages is there are similarities between languages, but yet there are so many differences. But a lot of times when people get excited about programming languages, they are keen at looking at the syntax. But one of the things I've realized over years learning multiple languages is syntax is something I never seem to learn so easily. Syntax comes from practice. The more I start coding in a particular language, the syntax comes naturally to me, and I kind of tend to memorize them with practice. But what is really important is that we take active time to learn the semantics of the languages. Because the semantics of the language is where the real power of the languages are, and also the differences and similarities emerge from the semantics. And semantics is something that you have to take active role in learning. It doesn't come so naturally like syntax does over time. So focusing on the semantics, we can think about what are the different capabilities of these languages. And what I want to talk about for the next several minutes is some things I've observed over time. One of them is we talk about languages that are statically typed and languages that are dynamically typed. While we talk about static typing versus dynamic typing and get excited about these things, it's important to realize that it is not just static versus dynamic that makes the difference. And I want to put them on the y-axis, and then I want to put on the x-axis the strong versus the weak typing. So what is the difference between these kinds of thinking? Well, static, of course, is when the type information is provided at compile time, or at least at code writing time, when you have languages like PHP, for example, where you don't compile the code. On the other hand, dynamic typing is also where code writing time, you don't specify these at the code writing time, but these information may be available at runtime. So in other words, is the type sanity determined when you are writing the code, when you are compiling the code, a point before the execution? Strong versus weak, on the other hand, is what happens during runtime. Is the code type sanity verified at the time of execution? Let's think about this for a minute. Take the example of Java. We all know that Java is statically typed language. But it turns out Java is also strongly typed, because when you execute the code, there are times when we get a class cast exception. Hopefully not too often. But we do get class cast exception at runtime because the JIT compiler and the runtime verifies the type information for you when the code is executing. So as a result, the type checking happens at runtime as much as at compile time in the case of Java. On the other hand, take the example of C++. Well, we know that C++ is a statically typed language. But what happens when you execute the C++ code? Well, whatever happens, happens. It's garbage in, garbage out. It's what is in the V table. Now, it's going to run and do whatever it wants to do. If you don't believe me, just watch any C++ programmer when in the morning before they go to work. They're very eager to go to work because they have no clue what the code is going to do when they get to work. And the point really is, that's an example of a code that is statically typed, but it's also a weakly typed language. Because weak typing, there's no enforcement at runtime, so is C and C++. On the other hand, if you take languages like Ruby and Python, for example, these languages, on the other hand, are dynamically typed. We don't say what the type is at code writing time, but when you execute the code, there is verification of type at runtime. So as a result, even though languages like Python and Ruby are dynamically typed, they actually are strongly typed as well, and you have certain amount of type checking at runtime. But of course, no talk will be complete without mentioning the best language humans have ever created, JavaScript. Now, what about JavaScript? Well, JavaScript, as we know, is dynamically typed. But what happens when you run the code? It's called miracle. It does things for itself. And so JavaScript is dynamically typed. It's also weakly typed. And I don't know who said this, but I saw this on Twitter, and somebody really said it very wisely. He said, JavaScript is weakly typed because every week I wonder what the code is doing. And so there's a reason why we have such a love for this language. And don't get me wrong, I love all languages. I love JavaScript also. Part of the reasons I make fun of languages is because I love them so much. But JavaScript, of course, is special. And I was programming with JavaScript one morning, and it refused to work, like a lot of code that refuses to work for me. But this one was a little bit more intimidating. And out of frustration, I posted this tweet. And here's my analysis of what JavaScript is. And here's how I want to define it. JavaScript is like an infant. It's cute to play with, but you have no clue why when it begins to cry. And so you're calling mom and saying, Mom, it's crying, what do I do? And mom says, have you fed the baby? Have you changed the diaper? Are there insects nearby? And that's how you debug JavaScript. You're trying to figure out what the heck is going wrong with it. So it's great when it's working, but when it doesn't, it can be really frustrating. But we are relying upon a lot of these weakly typed languages as much as strongly typed languages at runtime. But if you really look at the world we live in, both the front end and the back end are seriously supported by weakly typed languages, which is a bit scary, but the world hinges on them. But as you look at programming languages beyond that, we begin to realize that there are other similarities as well. Well, when it comes to languages, of course, there are different paradigms. Learning a language is easy, learning the syntax is easy, but changing a paradigm takes a lot of effort. In my career, I've gone through maybe about 6 different paradigm shifts, and every one of them have been very challenging and painful, but very rewarding once I made the shift. Well, of course, you have procedural programming languages. And then, of course, remember good old Dijkstra telling us go-tos are evil. We have the structured programming languages with clear structure of how these constructs are built together. Then, of course, we have object-oriented languages, and then we have functional languages as well. Now, when you look at these languages, you often wonder, is there anything that is similar between all these languages? Or are the paradigms so different from each other? And I realized one day that after all, there is really a nice common thread that connects all these languages. If you ask me, if we were to give an award, and an award to somebody in our field, and I would say hands down, that award should go to this one person who has influenced everything we do every single day. There is not a day, I'm saying this in all honesty, there's not a single day when I sit down to program, I don't admire and thank the words of the guy named David Wheeler. David Wheeler said, what's the most profound thing in our field? David Wheeler said, in computer science, we can solve any problem by using another level of indirection. This is phenomenal, isn't it? Because what do we do every single day? We solve problems and we use level of indirection over and over and over. So one day I got thinking, if David Wheeler is right, and I believe he is absolutely right, if he is right, then that should be a common thread that connects every paradigm of programming. If level of indirection is so important, Where is level of indirection in all these paradigms? And I was very curious about it, so I sat back and thought about it and started playing and experimenting with it. And so the question to ask is, what are the levels of indirection in these programming paradigms? Let's take procedural programming for a minute. So what is the level of indirection we use in procedural programming? And of course, we all know what that is, pointers. And we use pointers, and at one time, your pointer can point to a different structure or a different object. And as a result, you are able to, rather a different function, if you will, pardon me. And as a result, by having pointers to functions, you are able to vary the implementation of the function at runtime, whereas writing the code with the pointer. This is one of the things about language like C, is where we can create pointers to functions very effectively. Well, if that is the case, if pointers are so important, we should be seeing pointers everywhere, isn't it? Some of you may be thinking, oh, wait a minute, I program in Java. I don't use pointers, I use references. Well, the original creators of Java are the geniuses of the world, because they were looking at C++, which was the most predominant language of the time. And they realized that C++ programmers were not having fun time with pointers. And you don't go to a C++ programmer and say, pointers are great, that'll start a bar fight. So what they wanted to realize was they wanted to use pointers, but they know it wouldn't receive as much love. So they were the geniuses because they used pointers, but they called it references. This was amazing. And a generation of programmers started using pointers without knowing they are using pointers. So pointers are everywhere we turn because they are so fundamental to what we do. But what about object-oriented programming? Well, in object-oriented programming, that level of indirection is called polymorphism. Because polymorphism says, go ahead and use a reference to an object at compile time, but when you execute the code, we will call the function based on the real type of the object at runtime and not the perceived type of the object at compile time. So this gives you extensibility, and extensibility is the core behavior in object-oriented programming achieved through polymorphism. So polymorphism becomes that level of indirection in object-oriented programming. Well, that begs the question, if level of indirection is so critical to have, what would that be in functional programming? Well, it turns out functional programming has the same idea as well. Imagine for a minute that I give you an apple, not the machine, but a fruit. And if I give you an apple, there are 4 things you can do with an apple. You may be hungry, really hungry, and the instant I give you an apple, you could eat it right away, eagerly. Or you could take the apple and give it to a person next to you. Or you could save the apple for eating later on. Or you could simply throw it away. So whether you eat it now, give it to somebody else, throw it away, or save it for later is entirely up to you. But instead of giving you an apple, what if I give you a lambda? Well, a lambda is exactly the same. If I pass a lambda to you, you could use the lambda right away, execute it. You could pass the lambda to another function. You could save the lambda and run it later, or simply throw it away and not execute it at all. And so lambdas give you the ability to defer evaluation and have laziness in evaluation. So it turns out lambdas give you the level of indirection when it comes to the functional programming ideas. So this idea of using levels of indirection is so important and critical. We see this in every single paradigm of programming that we use. In that regard, with all these paradigms of programming, how do we go about proceeding with this? Well, it turns out a lot of times people talk about object-oriented versus functional style of programming. And I find this frustrating because the real enemy for us is not object-oriented programming. It has served us really well for a few decades. Now, clearly we can agree that we haven't done it all correctly or in a more sensible way, but the problem is not with object-oriented programming as it was created. So when I work with good friends of mine, there are some of them who believe that object-oriented programming is bad and functional programming is better. We are still friends. We go to dinner with each other. We just refuse to talk about this stuff. And the reason is, I believe truly that it's not a conflict between object-oriented programming and functional programming. The real question to ask is, are we really dealing with imperative style or functional style of programming? So one of the reasons is imperative style of programming is baked with accidental complexity. And that complexity that is inherent to imperative style of programming makes it really hard for us to write our applications. Functional programming, on the other hand, is based on declarative style of programming, and as a result, it removes that accidental complexity, or at least alleviates it. So in that regard, what is the difference between these two styles of programming? Well, it turns out in the imperative style of programming, we focus on telling what to do, and we focus on telling how to do it. So we get dragged into the details very quickly as time goes on. So for example, if you were to take a collection of people right here, and I want to let's say, print the names of everyone whose name is length 5, how do I go about doing just that? So what I'm going to do here is I'm going to start with this and say I equal to 0, I less than, and I have to think about, is it names.size, is it length, is it count? And that's not enough time in the day to make all these decisions. That is low-level detail. Or you might say, oh, you don't have to work so hard, Venkat. Simply say name comes from the names collection. Well, that's definitely a relief. But then I'm going to say, if name.length is equal to, and then you would tell me, no, you can't use double equals, you have to use dot equals. And the point is, you could be thinking through and decide whether to use a double equals or a dot equals depending on the data structure. That is a burden you have to take as well. So in this case, of course, because it's a primitive, I can say the length is 5. Then I'm going to simply output the name that is given to us and ignore the rest. So that becomes a part of an effort that we have to put in terms of how you have to write this code to go through imperatively every single step of the way. So in the imperative style of programming, you have to deal with not only the what you want to do, but get dragged into all these small, low-level details. All these little moving parts becomes your responsibility. Well, the nice thing about functional style of programming is that it is declarative. So in the declarative style of programming, you focus on what to do and not on how to do it. So the essence behind this is that functional programming is built on top of the declarative style. So one of the reasons why functional style is exciting is because it is declarative by nature, which doesn't have the accidental complexities we often deal with. So functional style is declarative plus the use of higher order functions. So in that regard, if I were to write this code using functional style of programming, the way I'm going to write this right here is to simply come in here and say, over here, say names.stream, and I can then ask for .filter. And I can simply say name.length is equal to 5, and then for each one of them, we can simply say system.out.println, and we can simply print it. So that becomes a lot easier in terms of the value that we want to work with, and providing the lambda right in there, we can execute the same output, but with a lot less effort. The code begins to flow like the problem statement in terms of how we are going to write it. So this becomes a lot easier to work with in general when we don't have to struggle through all the details, and we can focus on the what instead of the how. So in the imperative style of programming, we have to be dealing with all the details all by ourselves. And so imperative style is easy to read, but easy to write, but hard to read. Now, the reason for this is we have been trained so well ever since the beginning we start programming, a lot of times in imperative style code. So a lot of us find it very natural and easy to write imperative style code. But on the other hand, when you are asked to read somebody's imperative code, and that might be you after a vacation, it becomes really hard to read this code because you get dragged into all these details, and you're trying to really struggle with all the details buried into the code that you're looking at. On the other hand, I'm going to say about functional style is declarative. You focus on what and not how. And as a result, functional style is easy to read, but hard to write. And I'm saying it's hard to write because it's partly because of my unfamiliarity and lack of experience relative to and comparing to imperative style of programming. I'll be honest about it. I started programming in imperative style a few decades ago. I have been programming in functional style maybe less than half the time. And so it is natural for me to think in imperative style, not so much in functional style. I remember taking a flight from Europe to the US, and it was about a 9-hour flight. And as soon as I got into the flight, I took a problem, and I wanted to solve it with functional style. Today, I can solve functional style problems 50% of the time, almost instantaneously. The other 50% of the time, I got to struggle with it. On this flight, when I sat down, I wrote the code imperatively in about 10 minutes, and the code was working. And then I said to myself, I am going to write this in functional style. And I spent literally the next 8 hours of the flight trying to figure out how to write this code in functional style. Trust me, these kinds of exercises beat all in-flight entertainment. There's no reason to watch a movie when you can solve a problem like this. At the end of the 8 hours, I was like, duh, why did I not think of it? It is so simple to do, and it was instantaneous to think about a solution after that 8 hours of struggle. And when I look at the solution now, it makes so much sense, but arriving at it was not easy. It was a struggle for me. But maybe it's easy for somebody else because they have a better training or better thought process than I do. But in general, in my experience, it's not that natural for me. It takes me a lot more effort to write the code, but once it is written, it's a lot easier thanks to my familiarity now with the syntax and the semantics of functional style of programming. But on the other hand, imperative style of programming gets progressively hard over time. And this can be really annoying. Simple things must be simple, and more complex things should be, affordable. Well, in the case of imperative style, it can become really hard. Suppose we are told to print comma separated, the names that are of length 5. How do we write the code for it in the imperative style? You can start by saying string name coming from names, let's say. And then I want to say in this case, if the name dot length is equal to 5, then I want to print the name. That's what we started with. But I want to print the names, let's say, in uppercase. You can add a 2 uppercase to it. That was not hard at all. But I was told to print them comma separated. I can print them comma separated. But you know what they really meant? They want this to be on a single line when it's comma separated. And you can print them on a single line, comma separated. And when you do, what do you find? You find there's a stupid comma in the end. Has anyone seen the problem before? Every one of us. But the real question is, how did you feel when you saw that? And you said to yourself, this cannot be happening to me. That's the first reaction, isn't it? And then you said to yourselves, it's no big deal. I will strip out the comma. And then you realize, oh my goodness, how do you strip that comma out? If you put it into a string, string is immutable. And then you're thinking for a while. And then suddenly you say, you know what, it's not that bad. That's what we always say, right? It's not that bad. I can put this into a string builder. And the minute you say it, a colleague says, is a string builder or a string buffer? And you spend the next 2 hours arguing about it. And then somebody says, why were you struggling so hard? There's a very simple solution. Really, what is it? Oh, darn it. You just need to know not to put a comma in the end. Oh, that's the part I didn't realize. How do you do that? Very easy. All you do is go back to this code and say, int I equal to 0, I less than. 30 minutes later, we are still working on it, isn't it? Why? Because how do you know it's the last one? Well, it's not just the dot size is equal to. You got to know if there is nothing after coming after. And you're struggling with this. In the meantime, the boss comes to you and says, how's it going? And what do you tell the boss? This sucks. Well, let's try this again. The imperative style code becomes progressively hard as time goes on. What about the functional style? The functional style can take away some of those complexities for us because of its declarative nature. So you can say filter given a name dot length is equal to, and I'm going to simply say in this case 5, and then I'm going to tell this, well, collect this. And I'm going to say joining with a comma. The joining is coming from the collectors utility class, and I'm going to say collectors joining, and I'm going to ask it to join with a comma. And when we do it, of course, we don't have a comma in the very end. And you look at this and say, that is exactly how programming should be, just to focus on and get the work done. So the point really is that imperative style can get really annoying and complex over time. So if we stop here right now, we could go home with the conclusion that functional style is better than imperative style. We all should programming in functional programming. I've been wrong, and I've been wrong so many times in so many ways to so many levels. But it's okay to be wrong as long as we are willing to learn, in my opinion, and change our views as we learn better. And at one point in time, I used to think imperative was the best thing to do. And then I went overboard, and I thought functional was the best thing to do. And then I started realizing maybe that's really not true. There is a good place for both kind of programming, and it's really naive to say one way is better than other and only should be done exclusively. In a way, if you really think about it, programming should be imperative or should it be functional? And before we answer that question, let's think about something a little different, a little wider than just programming. Let's think of light. Well, about 100+ years ago, there were some very smart people who sat down to think about light. And they were asking the question, what is light? At one point, people like Einstein went on to say that light is a particle. Well, that was true because a lot of experiments done showed that light behaves like a particle. But then suddenly people started noticing that there were experiments that showed behavior of light that did not really fit into the definition of being a particle either. And that was very confusing. And now we know, of course, the rest of the story. And so is light a particle or is it a wave? And of course, we know that the science world has decided that this is called the wave-particle duality. I know that is a lot more exciting than functional versus imperative. But the point is, not everything in the world fits squarely in one place by a clear definition. And there are gray areas, there are duality we have to always deal with. So in physics and science, of course, we have come to agree the wave-particle duality. And I'm going to say we as programmers should really begin to agree that in programming we have the imperative-functional duality. And it is naive for us to claim that programming should be imperative or it should be functional exclusively. And it turns out that we should really be willing to mix and match imperative and functional programming at will. And there are some languages, as we know, only provide imperative style of programming. And we also know that there are some languages which only provide the functional style of programming. But if you look at a lot of languages out there in the world, especially languages that are relatively new or languages that have evolved in recent times, almost every one of those recent languages have been a hybrid programming language. Java, for example, Kotlin, Scala, Groovy, Python, Ruby, Smalltalk, keep going. A lot of these, including JavaScript, not to leave anything alone. And the point is, all of these languages are really hybrid programming languages. There is a reason for it. And I always say, language like Kotlin does not want to treat me like a child. It wants to treat me like an adult. It gives me these options and says, you pick what makes sense for you based on what you're trying, rather than we telling you that's the one right way to do. So we want to really embrace this imperative and functional duality. But what is the benefit of doing it? I'm going to say there are some really good benefit to embrace this duality because we can gain from them wherever it makes sense appropriately. I'm going to say imperative is really good at dealing with side effects and exceptions. If your code has side effect, you are able to really deal with it very effectively using imperative style of programming. In functional style, we want to write pure functions. You don't want to have any side effects. On the other hand, if you ask the question, how do you deal with exceptions? Well, the problem is not that the functional programming world, it's hard to deal with exceptions. The problem is exceptions are not a functional programming idea. Exceptions inherently are an imperative style of programming idea. What does an exception mean? You are going down the call stack, you run into an exception, you unwind the call stack to go back to the try block where it is being called, and you can handle it in the catch block. So the point is you are really imperatively walking through the call stack at that point. Now, on the other hand, programming in a functional paradigm is like a stream-based programming. There's a flow of the logic. You go from a pipeline of functions, a filter to a map to maybe another filter or whatever to a reduce. And this is kind of like driving on the freeway. If you're driving on the freeway at a high speed and you have a flat tire, what's the worst thing I can tell you? I can tell you, you have a flat tire, now you have to drive in reverse and go back to where you came from. No sensible person will tell you that. You have a flat tire, you safely get down to the shoulder. So the point really is, when you are dealing with the error state in a functional pipeline, you don't want to roll your call stack. Instead, you want to exit safely and deal with it. But unfortunately, this is so incredibly hard to do in a functional pipeline. Functional programming is really good for dealing with scale and parallelization and for us to reason the program. So while functional has a lot of benefits, it doesn't do really well certain edge cases that we really need to deal with in programming that imperative style deals with a lot better. So the capability of the modern languages that we are dealing with is that it embraces the two styles of programming. For example, if I were to take a code like this one right in here, one of the beautiful things about this is, how do we go about parallelizing the code? Imagine for a minute that we have written the code using a traditional for loop or while loop and things like that. And if I wrote with the for loop or a while loop, you're going to have shared mutability in your code potentially. And you have written this code, and you've taken all the time to write this code using sequential programming. Now, how do you know you are using you're writing sequential code? I'll tell you one way to clearly know you're writing sequential code. When you go to work, everybody smiles at each other. That's a sign you're writing sequential code, because it's easy to write, easy to manage, easy to debug, and everybody is happy. You go to lunch as a team when you write sequential code. And one day somebody comes to you and says, you know, the code is not performing really well. We should make it faster. And you're sitting there and struggling. How do you make it faster? And somebody tells you we should use multi-threading with a for loop and a while loop. That's the last day anyone smiled at work. And you spend all the day and night debugging the code. Forget about going to lunch, leave alone team lunch. And of course, this code turns into a monster. And the day you introduce thread is that innocent, beautiful looking code turns into a monster. And the structure of the code is no longer the same. And you look at this code and you cannot recognize this anymore. And you stare at this code and you are absolutely nostalgic. And you say, back in time when this code was easy to maintain. And you don't want to go to work another time because it's so boring to be debugging this code. And with all these locks and synchronized blocks, it becomes a nightmare. I give that type of programming the synchronize and suffer programming model. And it becomes really painful to deal with. But the real cool thing about Streams API is, at least for a collection of data, the structure of sequential code is the same as the structure of concurrent code. When I run this code, it produces the result. If this was a large collection, if it really deserves parallelization, I can make the decision to parallelize it, but the implementation is absolutely trivial. I don't have to work that hard, because all I have to do is make it parallel, and it runs in parallel. But notice the structure is exactly the same as it was. So the structure of sequential code, the structure of sequential functional code is the same as the structure of concurrent functional code. And when the code structure is exactly the same, there are a lot of benefits. You can write the code sequentially. You can debug the code. You can experiment with it. You can reason it. And if the performance is adequate, leave it. But if you need something different, you can parallelize it with almost no effort. And so you get to reap the benefit of performance without enduring the pain of changing the code. And that, to me, is phenomenal. And this is one of the things that drew me into the Streams API, is that the structure of sequential code is identical to the structure of the concurrent code. But this is true only as long as you don't deal with exceptions. The minute you deal with exception, what happens? Well, the exceptions break the flow. You know, people often tell me Java doesn't support exceptions properly in Stream. There's a good reason for it, because it doesn't belong over there. When you look at languages like Haskell and Scala, what they do is to introduce a maybe monad, and they try to handle it. My argument is, while they try to handle it, it breaks the flow of the code. It doesn't make the code cohesive more important. And to me, what good is a good, beautiful code that turns into an ugly code to maintain and loses cohesion when you start changing it? So when it comes to exceptions, I refuse to program with functional style. That is when I eagerly fall back to imperative style of coding, because I feel that is the right choice. So when my code doesn't have side effects, when my code doesn't have exceptions, I tend to think and program functionally. But when my code deals with exceptions and or side effects, I am perfectly okay to fall back to imperative style and program in it. But there is another benefit that imperative gives us. And to explore this, let's think about something a little bit when it comes to the imperative style of programming. And I'm going to use an example here from JavaScript. I know that's a little scary, but I think we can learn from everywhere. So here is a compute function I'm bringing into JavaScript. And this compute function, doesn't matter what it does, but it's going to be sequential execution. And I'm going to make a function call. It's called call function. I'm going to write this function called call. In this function, I put a try and a catch block. Clearly, this is imperative style of programming. And within the try block, I'm going to make a call to the compute function. When the compute function gives me a result, it's a sequential call, and I'm going to simply go ahead and call, say made the request, and then wait for the, well, obviously we already waited for the response, made the request, and I print the result. What if something were to go wrong? I'm going to simply handle the exception right there and print it. And of course, I want to make the call to this function, and that's what I'm doing in the end. This is a very simple sequential code as we can think. Now, in this case, of course, if I make the call to the function as being a sequential code, it will fully run the compute function before it comes to the made the call. And you can see that pretty nicely here. Compute called, made the request, and that is the sequence. It is sequential. But I want to make this code asynchronous. And I'm going to bet my money on this. In Java, we've been focused on parallelism for a long time. And don't get me wrong, parallelism has its use. My dissertation was related to parallel processing. So I'm not telling you parallelism is not important. But we've been putting all our effort towards parallelism in Java, and we have almost ignored the asynchronous programming. And I'm going to bet today that in the future, in the next 5 years, one of the most important things we're going to do with Java is non-blocking asynchronous call and not as much as parallelism. With the world we are moving into with microservices and big data processing and reactive programming, asynchronous programming is more important, in my opinion, in the long run than just parallelism. So as a result, we want to really embrace asynchrony. This is one of the reasons I'm really excited about Project Loom that's coming in Java. But we'll get a taste of what it would feel like doing asynchrony and why imperative style of programming shines in that regard. So in this case, of course, when I run this code, you can see it says compute called and made the call. This is, of course, a synchronous code. But I'm going to switch over here to another file. I'm going to take this code. These are two separate files right now with exactly the same code. But I'm going to come in here and make this as a compute async. In the case of JavaScript, compute async is returning promise. Well, promises in JavaScript are nothing but completable future in Java. But completable future, one of the nice things it provides for you is the ability to do functional pipeline like promises does in JavaScript. But both in JavaScript, while promises exist and give a nice functional pipeline, they decided to introduce something a little different. So to execute this particular code, this is returning a promise. But what I can do is I can wrap this function with an async right there and tell the translator that, hey, there is an asynchronous operation happening here. And then I can come back and await for the result that I'm going to get at this point. So by doing this, what is the benefit I get? By using the await, I'm saying, wait for the asynchronous call to be done. When I execute this code, notice the first line is made the call, and then the operation executes. So line number 6 executed before the details of line number 5 executed. But what excites me about code like this is the structure of asynchronous code and the structure of concurrent code is absolutely identical. So while you can keep your code imperative in nature, you can switch between asynchronous versus asynchronous without losing our mind. We don't have to rewrite the code to be asynchronous. You write the code in a synchronous fashion, and when you want asynchrony, just decorate it, and you can make it asynchronous. And as a result, just like what we saw with the parallelization, we can preserve the structure of the code with asynchronous as well. Let's entertain this thought just a little bit to move a little further. I'm going to take one example of how this would look like in writing code, and I'm going to show an example here in Kotlin. So in Kotlin, I want to create a function, first of all, to show the thread information of this function. Well, in Kotlin, you say function fun task 1. Well, the reason is Kotlin wants you to remember to have fun every time you write code, so you put a fun in there. And then, of course, I'm going to print out entering task 1. That's what I'm going to say. And I'm going to say from thread, and I will simply print out the thread right here as current thread. So that way we can know what thread is executing it. So entering task 1 from thread, and of course exiting, I'm going to say task 1 from the thread as well, and the same thread. That's all I'm going to do for task 1 at the moment. And here comes the task 2 I'm going to execute, and I'm going to say this is task 2, and this is going to be task 2. I want to make a call to these two functions. So I'm going to simply say run task 1, and I'm going to call task 2. But I'm going to print out a call to them, and I'm going to print out the thread.current thread over here. This is kind of easy to see what's going to happen. When I run the code here, you will notice that in this code we have entering task 1, exiting task 1, entering task 2, exiting task 2. And then, of course, it says call them. This is pretty darn sequential, no surprises over here in this code. On the other hand, I can take this idea and say, I want to run them in asynchronous mode using coroutines. And coroutines are an integral part of Kotlin right now. So I'm going to say import kotlinx.coroutines. And in this case, of course, I'm going to ask it to say run blocking. This starts off a coroutine, which is going to wait until the coroutine completes, that it completes. So when I run the code, there is really no difference in the output. It is exactly the same as it was a minute ago. And you can see that sequential code running all in the main thread. But on the other hand, we're going to do something a little different. I'm going to come into this code. I'm going to call over here a launch. And then this launch over here is going to set off these two to execute in a completely asynchronous manner. We go into a non-blocking operation. So because it's non-blocking, you're not going to wait on it. It's like going to the coffee machine to get some coffee. If there's no coffee, you turn on the machine, but you don't wait for it. You walk around and do other things, and then you come back and get your coffee. So you want the code to be non-blocking. Notice I did not change the structure of the code. I just simply said launch. That's all I did right now. When I execute the code this time, you will notice that the first line printed here is called them. And then it entered and exited task 1 and entered and exited task 2. So in this case, you can clearly see that we made the call asynchronous. But one of the cool things about coroutines is you can go from concurrency to parallelism really well. Let's think of the difference between concurrency and parallelism, if you will. And for this, I'm going to ask for a volunteer. Maybe this gentleman here on the phone. Can you help me for a minute? All right. Thank you. What's your name, sir? Left. Awesome. How are you doing today?
Nice.
Nice? A little nice or really nice? Let's walk a little bit. Little nice or really nice? He's like, I was nice until you called me. Right? Let's walk a little bit. Are you enjoying the conference? That's not good. All the CPUs are busy processing.
Yes.
Are you enjoying? Is the weather too hot for you?
I'm enjoying.
You're enjoying the conference.
Yeah.
Is the weather too hot for you?
No.
No, it's good? Yeah. So, we are walking in parallel. Well, even though there's a little delay in one process. We're walking in parallel. Would you agree we're walking in parallel?
Yeah.
All right, we're walking in parallel. But we are talking concurrently. Would you agree with that?
Yes.
Because I'm not speaking over you. You're not speaking over me. I say something, and you reluctantly say something back. Would you agree?
Yes, I do.
That's an example of concurrency versus parallel. Does that make sense? We both walked at the same time, but we are speaking at the same time, but you a little bit, me a little bit, and that becomes concurrent. Thanks for helping me with this. Appreciate it. Give lift the high hand. Thank you. So this shows two things: how concurrent and parallel differs, and why you should never sit close to the stage anymore. So hopefully that gives you an idea about how these two things behave. So when it comes to parallel, you have multiple things going on at the same time. He was walking along with me. We both were walking at the same time. On the other hand, I spoke and yielded to him. Oh, the word here is yielded. Keep that in mind. I spoke and yielded to him, and he spoke and yielded to me. So what we can do is we can do concurrent versus parallel very easily. So when I run this code, notice all this is running in the main thread. That's what we are doing. The main is running everything. But I'm going to go back here and say yield, so I can yield to another process. And I'm going to go here and yield as well. Now, because I'm yielding, Kotlin wants you to know that this is not a normal function. This is the function which is going to entertain coroutines under the hood with continuations. And so they want to annotate the code. And they're going to annotate this just to give you a clue that this is not a normal function, which is great. But I do have a formal complaint to make. I sincerely think they should have chosen a better keyword. Because to say that, you use the word suspend fun. That's wild. That makes me sad. Why would I want to suspend fun? But in any case, this is going to simply say, this is a suspendable function. That's what you're saying. But now that I marked the function as suspend, and I said yield, I am going to say something, and I'm going to yield to him, for him to say something before he yields back to me. So when I execute the code all of a sudden, you notice from the output, we are concurrent. Notice that I said called them, then I entered task 1, but I have not exited task 1 yet. But in the same token, in the main thread, I've entered task 2. And then, of course, I exit task 1, and then I exit task 2. So all of a sudden, at the same time, the main is in 2 methods, or it appears to be in 2 methods, both in task 1 and task 2. Much like all of a sudden it appeared like both of us were speaking, and true, we were. Except I was yielding to him, and he was kindly yielding to me, and we were talking at the same time, but not over each other. We were pretty civil to each other. And that is exactly the point is, you can build this kind of concurrency. But if you want to make it parallel, all you have to do is provide a different threading context, and the functions will then run in a completely different thread at that point. But what we saw in this exercise was that the structure of the synchronous imperative code can be the same as the structure of asynchronous imperative code. So one of the benefits we get in this case is to go from a synchronous to an asynchronous, you don't have to change the structure of your code. The code structure can be exactly the same as you move forward, and that becomes a lot easier to communicate the intent. So you can write the code synchronously and then refactor it or change it to being asynchronous, as the case may be. So the languages should enable and not limit the form of expressions. And this is one thing I'm very keen when it comes to choosing what programming paradigms to use and to choose the language to program in. And I want the flexibility, not the limitations. So the language should give me an enable and the form of expression, and give me the ability to choose the form of expression that's right for the problem at hand. In a way, I would say, to me, languages are like this hybrid. We can have this hybrid of, a hybrid plane. It is up in the air. It can also be on top of the water, as the case may be. What if we consider a language to be like a thermostat, where we can dial this all the way down and make it cooler, which would be really nice for a day like this, which is so hot. Or we can turn it all the way up and make it warmer in a deep winter. or maybe leave it somewhere right in the middle where it's comfortable. And every one of us can choose and adjust this based on what that level is. And if we can have that ability to adjust this, then I don't compel myself to say, this is the only way I will program. I have the freedom to choose, and freedom to choose based on the problem I'm solving. And when I pick up a different problem to solve, I have the absolute freedom to choose the paradigm and the style that makes sense for that problem. And I'm no longer limited by what is dictated on me. And I can use my strengths along with my team to decide what the right one is. So in a sense, what I'm getting to is that we have to really reconsider what we think. And as I've said already, I'm wrong in several ways, but I want to learn and change what I think about as time goes on, as my knowledge improves. After all, as Bernard Shaw said, progress is impossible without change, and those who cannot change their minds cannot change anything. So I'm not suggesting to be whimsical, but what I'm saying is that we should learn these things, but be willing to accept that there are differences. After all, I would argue wisdom is realizing that there are no absolutes. So anytime we want to seek absolutes, I think we failed really badly. And so I would just end by saying, wisdom is realizing that there are no absolutes. Hope that was useful. Thank you.